This instruction is on the finding the stress concentration factor for an element of material beside a hole in a beam and bending. The definition for stress concentration factor is the maximum stress in the vicinity of the hole divided by the nominal stress. That would normally be there if the stress concentration factor didn't exist. Now, the way this works is we're going to do this using strain gauges, so we will actually end up with a maximum strain and a nominal strain. In order to place strain gauges to find the nominal strain, this is the maximum strain and this will be the minimum strain. Somewhere between there, this is higher than the nominal, this is lower than the nominal. Somewhere in there is nominal, but we don't know how to place a strain gauge to exactly measure the nominal. So we're going to do a little manipulation where we can equilibrate, we can find mathematically where to locate a strain gauge in order to measure the nominal strain. The nominal strain, if we write the equation for it, is m over s. The m will be p times l, this p times that l, out to where the hole is, divided by, and so all of this is the section modulus for the hole, for the cross section when the hole is cut out. And we can write the amount of strain or stress for a cross section without the hole and put it at a different location, L. So here's cross section A, and it's a distance L away. And so its equation would be the same, except the hole is not cut out for the section modulus. And our goal is to make these two equal to each other. So we simply set those mathematically equal to each other and manipulate the equations to find that a ratio of L over L will be just simply a ratio of the dimensions of the beam and the hole, of the cross-section of the beam and the hole. So that will tell us capital L, in other words, where we can place this strain gauge, this strategic location to place strain gauge A, so that it will read the same and equivalent strain as the nominal strain if we tried to place it beside the hole. So that's what we're going to do. We're going to read strain gauge A, and that will be the nominal strain. So we know where we're going to get that value. We know where we're going to get that one. It's just straight off strain gauge A. And then now we need to figure out where we're going to get the maximum strain. Now, the way we're going to do that is we're going to do a relationship, and we're going to put 3 tiny strain gauges beside this hole. And we're going to measure those. That's these strain gauges. And we know how far away they are from the edge of the hole. So we will be able to make a ratio of the radius of the hole to the distance. In other words, a ratio of r over x. And if we, because this is nonlinear, if we square that, we can measure these initial, final, and this is the number that we're going to use for our plot. And if we plot that so that the amount of strain read on the gauge, that's actually in microstrain, and this axis is r over x quantity squared, we will be able to plot, and this is a power plot, by the way. When you do the trend line for that, it needs to be a power trend line on your Excel plot. And notice that if we take r over x and make it equal to 1, that will tell us, this would continue to go up, that will tell us the strain that would occur at the edge of the hole. So that's going to be our maximum value. So what you need to do is take this equation, get the trend line to print the equation on your chart, and take that equation and extrapolate it so that r over x, that x in there is actually represents r over x, is equal to 1. That will give you the maximum value. One thing that happens when you do this is those strain gauges have different gauge factors, and so it needs a correction factor, and I've already done that for you. If this number is 2,000, then that's the corrected value. Don't use 2,000. Use 1967. Now, in order to compare this to published, you'll need to go to Rourke. I give you the reference for that, and use this plot with this relationship to show how much stress concentration occurs for a hole in a beam in bending.